Myself, Dr. Mohan Sangle. I am the Associate Professor in Rayat Shikshan Sanstha. Today, my topic is the gas chromatography. Gas chromatography is a separation technique. Here, the gas is used as a mobile phase. Therefore, it is called as a gas chromatography. The chromatographic technique is firstly discovered by the botanical scientist Michael Twist in 1906. Here, two phases are there. That is, one is the stationary phase and another one is the mobile phase. If stationary phase is a solid and mobile phase is a gas, that is called as a gas solid chromatography. If stationary phase is liquid and the mobile phase is gas, that is the gas liquid chromatography. In gas chromatography, thousands of applications have been reported in organic, general, and biochemistry. It has been applied to a wide variety of theoretical and practical problems in the separation and identification of components of the atmosphere, gases, liquids, drugs, and the commercial product. The method of separating volatile or gaseous substances by using gas as the mobile phase is called as gas chromatography. In GC, the stationary phase used may be solid adsorbent or a non-volatile, that is high boiling liquid held on the solid surface. Therefore, it is mainly divided into two types, that is gas solid chromatography and gas liquid chromatography. In gas solid chromatography, when stationary phase is a solid which is having the large surface area while the mobile phase is a gas. This technique is called as a gas solid chromatography or GSC. Here, in this process, a sample between the mobile gas phase and the solid stationary phase the are separated. Generally, the solid stationary phase are used as a silica gel, alumina, charcoal, molecular sieve, inorganic salts, minerals, porous polymers, etc. In gas liquid chromatography, when the stationary phase is a non-volatile liquid coated on inert solid and the mobile phase is a gas. The technique is called as a gas liquid chromatography. In this technique, the separation of volatile or gaseous substances occurs by partitioning a sample between a mobile gas phase and thin layer of non-volatile liquid coated on the solid support. In gas chromatography is quite similar to column chromatography except that a gas is used as a mobile phase instead of a liquid. In GSC is based upon the selective absorption on a solid, whereas in GLC is based upon the partition between the gas and the immiscible liquid phase. In GSC was developed in 1943, while in GLC is developed in 1951. It is more popular and has many more applications than the GSC. It separates the complex mixtures of gases or volatile organic compounds. The main advantage of gas chromatography are the technique is suitable for routine analysis because the operations involved are simple. The sensitivity of method is high, hence require very small sample. Time required for analysis is less and the separation power of GC is very high, hence very complex mixture can be separated. The important condition for GC: the sample used in GC separation must either be a gas or capable of being converted to a gas at the temperature of the column. Sample should be converted immediately into gaseous state and the substance should be soluble in proper solvent. The separation mechanism is based on the height equivalent to theoretical plate. Therefore, the, the equilibrium reaction of substances between the mobile and stationary phase represent the one theoretical plate is called as a separation efficiency of the column. Therefore, the number of theoretical plates and the column length is related to the height equivalent to theoretical plate. In short, it is called as a HETP. Mathematically, it is given by the equation HETP is equal to column length divided by number of theoretical plate. Mathematically, we have to determine the number of theoretical plate. N is equal to 16 tr upon w bracket square, where n is the number of theoretical plates, tr is the retention time, w is the peak width measured in unit of tr. Instead of tr, that is retention time, retention volume, that is vr, can be used in the above equation. This is the chromatogram. It is represented, it is plotted, that is detector response versus time. This chromatographic gas peak is used for the detection of the constituent as well as the concentration of the constituents. Then the alternate equation for the determination of number of theoretical plates is also calculated by the mathematical equation n is equal to 5.55 tr square divided by w1 half, that is half peak width bracket square. Therefore, by applying the van der Waals equation, HETP is equal to capital A plus B upon U plus W. Therefore, these ABC are the constant. U are the average linear velocity of carrier gas in centimeter per second. So, ABC illustrated in the figure, that is this figure shows it is the value of A depends on the packing of the particle in the column. Here we have seen the principle of the gas chromatography. This principle is mainly depend upon three laws. First, Henry's law, second, Friendly's isotherm, and third one is the Langmuir isotherm. When a gas or vapor comes in contact with the solid, that is stationary phase, a fixed amount of gas it dissolves in liquid according to the Henry's law distribution. Mathematically, it is written x upon m is equal to Kc. While when a gas or vapor, that is adsorbate, comes in contact with an adsorbent, that is solid stationary phase, certain amount of it gets absorbed by it. This adsorption takes place according to the quantitative relation known as Friendly's isotherm or Langmuir isotherm. The Friendly's isotherm mathematically explain x upon m is equal to Kc raised to 1 upon n, while Langmuir isotherm is mathematically explained x upon m is equal to Ac upon Bc plus 1, where x is the mass of a gas or vapor adsorbed, m is the mass of adsorbent, x upon m is the mass of gas or vapor adsorbed per unit mass of the adsorbent. C is the equilibrium concentration depending upon the adsorbate or adsorbent at the given temperature. A and B are the constituents. In both cases, the processes are selective and there are different constant values for the different gas or vapor adsorbent pairs. In separate the gas or vapor constituent from their mixture. The separation in GLC is thus based upon the relative distribution, that is partition of the sample component between the stationary liquid phase and a mobile gas phase. Thus, GLC is a partition type of chromatography. The principle of GLC is almost similar to that of liquid-liquid partition chromatography, except that the mobile phase in GLC is a gas rather than a solid. More volatile compounds having the greater vapor pressure move more rapidly and come out from the column before the less volatile ones. Thus, GLC separation is carried out by distribution of a sample between a thin layer of non-volatile liquid held on the solid support and the mobile gas phase. The GSC and GLC are differentiate on its stationary phase, on its mobile phase, on its adsorbing capacity, on its partition capacity. Therefore, this chromatography is two types. Here, the instrumentation of the gas liquid chromatography. The basic component of gas chromatography are as follows. The first one is the tank of carrier gas. Second one is an injection port for the sample application. Third one is the column. Fourth one is the detector with the suitable readout system. Therefore, the chromatograph with a chart recorder. Here, this is the figure. In this figure, the cylindrical portion, cylinder, this is wire gauze, then this is column, dotted line, and it is connected to the detector, amplifier, and recorder. The working, due to the different partition coefficient of the component, the separation takes place between the stationary phase and the mobile phase. The sample injection port, column and detector are heated to suitable temperature so as to prevent consideration of the sample. The separated components come out along with the mobile gas phase at the other end of the column. They are directly passed into the detector system which is attached to the other end of the column. The separated component come out at constant flow rate from the column and they automatically detected in the detector. There are many types of the detector like TCD, that is thermal conductivity detector, FID, that is flame ionization detector, and ECD, that is electron capture detector. The detector gives response to the readout system. The magnitude of the detector response depend upon the composition or concentration of vapors. Every detector possesses two sides. One is the reference side and another one is the sample side. The carrier gas is first passed to the reference side, then it enter the column and then it comes out from the column through the sample side. The response of the sample side relative to the reference side is fed to a recorder system. That is, the output from the detector is fed to the recorder which produces a pane trace called as a chromatogram. Here, the tank of a carrier gas. Generally, the carrier gas are hydrogen, helium, argon, nitrogen, and air are used as a carrier gas. The choice of carrier gas is depend upon the nature of mixture to be separated and detector used in the instrument. Hydrogen has more advantages but dangerous to use since it may be react with unsaturated compound. It may catch fire and give rise to hazard of explosion. Helium is the second best carrier gas used in GC, but its cost is high. Helium is mostly used because of the greater thermal conductivity, low density, inertness, and greater flow rates. Nitrogen is less expensive but gives rise to decrease in sensitivity of technique, and air is used when only when oxygen in air is useful for the separation of the detection. While selecting a carrier gas, it must be satisfy the following condition. It should not cause the risk of fire or explosion hazard. It should be readily available in high purity. The flow rate should be high so that the speed of analysis is maintained. It should be suitable for the detector employed and the type of sample to be analyzed, and it should be inert. Here, the injection port of the sample. This is the figure of the injection port. The sample is injected with the help of the syringe. It consists of a small chamber having an inlet into the column. The chamber has a self-sealing silicon rubber septum. It is attached to one end of the column. The carrier gas also passes through the one side of the port. The arrangement used to introduce the sample mixture into the gas mobile phase is called as a sample injection system. The gas sample can be directly injected through the septum into the column with the help of gas light. Syringe. Liquid samples are introduced using microsyringe with the hypodermic needle. The needle is inserted through the rubber septum and the sample injected smoothly into the heated metal block at the head of the column. The temperature of the injection port should be such that the liquid is rapidly vaporized but without decomposing the sample. The injection of the sample solution by microsyringe through the rubber septum into the packed circular column are shown in this figure. Look, this is the figure. This is above is the syringe, and here is the metal block which is seen in the cross link, and here is the rubber septum, and then column dotted line shows the column. The chromatographic column, it is made up of a glass or metal tube. The length of the column is 2 to 3 meter and diameter is 2 to 4 meter. It is in the form of circular path for 3 or 4 turns and placed in the temperature control oven or thermostat. At the end of the column, the mobile gas phase is passed through an injection port. It is shown in the figure. The column is packed with the powdered solid support. The solid support consists of uniformly sized particle and must be stable at column temperature. The fire brick or kieselguhr or silicate, that is diatomaceous earth, is used as a solid support material because this is stable at the high temperature. The function of solid support in the packed column is to provide an inert surface on which stationary liquid phase can be coated. The stationary liquid phase like the hydroxyl acid, glycol, glycerol, polyglycol, dino dinomniphthalate, silicon gum rubber, squalene, epizonal grease, paraffin oil, that is called as a nuzol, can be used as a stationary liquid phase. The column packing is prepared by adding the correct amount of liquid phase dissolved in suitable solvent to a weighted quantity of the solid support in a suitable dish. Acetone or dichloromethane can be used as a solvent. This volatile solvent can be removed by spontaneous evaporation of the final traces of the solvent may be removed under vacuum. The solid support should remain free flowing after being coated with the liquid phase. The liquid phase substrate must have a good solvent property, different partitioning property, low vapor pressure and high thermal stability. The substrate like glycols is used for the solute like amines, ethers, alcohols, ketones, aromatic compound having the temperature range 100 to 200 degrees centigrade. The substance like paraffin, that is nuzol oil, is used for the solute like paraffin, olefin, halides having temperature range 150 degrees centigrade. The substrate like silicon oil is useful for a solute like paraffin, olefin, ester and ethers having temperature range 200 degrees centigrade. The substrate like dedecyl phthalate like a polar compound having the temperature range 170 degrees centigrade. In the gas chromatography, three detectors are used First one is the thermal conductivity detector, that is TCD. Second one is the flame ionization detector, and third one is the electron capture detector. The choice of detector is depend upon the nature of carrier gas used as a mobile phase, the chemical composition of the sample, and hence the nature of separated components, the concentration of the sample component. For example, thermal conductivity detector is used for measuring the concentration in micrograms, while flame ionization detector is used as a picogram concentration. Here, first we have seen the thermal conductivity detector, that is TCD. This is the figure of the thermal conductivity detector. In the thermal conductivity detector, there is inside the arrangement of Wheatstone bridge, and there is having the two system. One is the sample site and another one is the reference site. In the thermal conductivity detector, it is also known as the hot wire or cathometer detector. It works on the thermal conductivity of high resistance wire, of which conductivity depend upon the temperature, that is the thermistor. In this detector, two pairs of matched filament are arranged in a Wheatstone bridge circuit. These two pairs of heated metal filaments are enclosed in two separate small metal chambers. Through one chamber, pure carrier gas is allowed to pass, that is reference side, while through the another chamber, effluent from the column, that is carrier gas, and the sample is allowed pass through the sensor, that is the sample site. The filament possesses high resistance and it varies with the temperature when through both the chambers carrier gas is allowed to pass. The temperature of the filament in the both chamber remains the same and bridge is balanced and no signal is generated. But when the effluent from the column consists of vapors of the sample, then the rate of cooling of the filament sensor changes, which results in the temperature imbalance between the reference and sensor. The signal is generated due to temperature imbalance in the bridge. The extent of imbalance of the temperature in the bridge is a measure of concentration of vapors of the sample in carrier gas. The generated signal is fed to the chart recorder, which record a chromatogram. The TCD has several advantages as compared to the other GC detector. It is universal detector, that is, it responds to all substances except carrier gas. It is not destructive. Sample component can be collected for further use. It is very simple to operate. One is the most important limitation, the sensitivity of this detector is low. The second detector is the flame ionization detector. This detector, it consists of a small hydrogen flame burning an excess of air and surrounded by the electrostatic field. The thermal energy in the hydrogen flame is sufficient to cause many molecules to ionize. The effluent gas from the column is mixed with hydrogen and burned at the tip of the metal jet. Excess of air. A potential is applied between the jet itself, that is cathode, and second electrode located around the flame, that is anode. The ions are formed in the flame due to thermal decomposition of molecule of the sample component. The burner jet is the negative electrode, while the anode is usually a wire or a grid extending into the tip of the flame. The ions produced are collected at the electrode and the resulting ion current measured after the amplification. Initially, the combustion of the carrier gas, hydrogen and air produces very few ions and essentially a constant signal is obtained. This is the figure of the flame ionization detector. Here the flame is there inside and this is one is the sample insert side directly pass on the flame. The third detector is the electron capture detector, ECD. The principle of electron capture detector is based on the electron absorption by compounds having an affinity for free electron. In this detector, column passes over a beta emitter source, usually nickel 63 file or Fe55 file used as a beta emitters. When a carrier gas when interact with the beta particle, energy of beta particle is sufficient to ionize carrier gas and produce a large number of electrons. The electron emitted due to ionization are captured by positive collector electrode and cause an electric current to flow an external circuit. The current is amplified and recorded. This is the electron capture detector. Inside there is a beta source. The characteristics of this electron capture detector: it can be used at high temperature, that is 350 degrees centigrade. Two electrodes are used. One is small metal coated with nickel or tritium. Nitrogen is used as a carrier gas since it has lower excitation energy than argon. It is extremely sensitive to the molecules containing electronegative atoms such as halogen containing compound, but it is not sensitive to hydrocarbon. The compounds having low electronegative atoms can also be measured by preparing their derivative. The molecule having electronegative atom can only capture the electron and form ions. In the gas chromatogram and the qualitative quantitative analysis, the study of chromatogram, first one is the chromatogram. The chromatogram is a plot of detector signal, that is the response against time. It consists of a series of peaks. Each individual peaks corresponds to each component detected in the sample. Second one is the retention time. It is denoted as a TR. It is defined as the time required for the component to come out from the column after the injection of the sample. It is used or useful for the quantitative identification of peak area for concentration. It is a characteristic property of the component. It is useful in the qualitative identification of the component of a given mixture. It depends upon the nature of stationary phase as well as mobile phase, flow rate and the column temperature. The retention time TR is determined with the help of D, that is distance upon the chart speed. The detector response recorded versus time, the peak is obtained called as a gas chromatogram. The measure of the ability of chromatographic column to separate the component of a mixture is called as a efficiency of the column. The rate of migration of solute and the development of peak in the chromatogram can be explained by two theory. One is the plate theory and second one is the rate theory. According to the plate theory, a chromatographic column consists of a series of discrete yet continuous horizontal layers called as a theoretical plate. In the plate theory, the separation efficiency of the gas chromatographic column is expressed in terms of a number of theoretical plates denoted by N in the column. The column efficiency can also be measured by the height equivalent of the theoretical plate denoted as a HETP or capital H. The HETP is the length of column corresponding to a single theoretical plate, thickness of one plate, that is the height of one layer of the column. It can be calculated from the height, that is L, capital L of the column and the number of theoretical plate within the column. Here the figure shows in the first figure single peak and in the second figure there are three peaks. This is the chromatogram. In the first figure, from the figure we have shown only one component, and from the figure second it is three component because three peaks are there. Similarly, the retention volume is also determined. Retention volume is mathematically is calculated. VR is equal to TR multiplied by flow rate of carrier gas, FC. That is, VR is the retention volume, TR is the retention time and FC is the flow rate of the carrier gas. Finally, we come to the application of the chromatography. GC, gas chromatography, is applicable as a qualitative analysis, quantitative analysis, as a metal chelate analysis and the miscellaneous application. In the first qualitative analysis, from the chromatogram we can easily identify the retention time, Qualitative analysis is also done comparison retention time or retention volume of the sample component with retention time or retention volume of the reference compound developed under identical experimental condition when GC can be combined with the another technique like a mass forms GCMS technique. Gas chromatography, mass spectrometry technique, which is a very powerful technique. And secondly, the quantitative analysis. The response of detector recorded system is linear with respect to the concentration of solute and the factors as such the rate of carrier gas flow, column temperature, etc. They are constant. Then the recorded peak area or the peak height in the chromatogram is proportional to the concentration of the sample component. For qualitative estimation, the condition should be: first, response of the detector and recorder must be linear with respect to concentration of solute. Second, factors such as rate of flow of carrier gas, column temperature should be kept constant. Third, the effect of variation must be eliminated. The peak area can be calculated by one of the following technique. First, that is a geometrical method. Second, the perimetry. Third one is the integration of weighing. Fourth one is the automation integration. And fifth one is the data evaluation. In the third application, the gas chromatography is useful for the metal chelates. In gas chromatography, samples should be sufficiently volatile, thermal stable, and should form a neutral metal chelate, generally beta diketone ligand, for example acetylacetone, and fluorinated derivative from stable volatile chelates with aluminium, beryllium, chromium third, and the number of other metal like beryllium forms volatile beryllium trifluoroacetyl acetone chelate, while aluminium and chromium third form their volatile acetyl acetonate. In the fourth, that is the miscellaneous application, GLC is used in the detection of steroid in blood sample of the athletes. The analysis of dairy product for aldehyde, it is also used in ketone, fatty acids, milk sugar, etc. The DLC used in the analysis of food products such as pesticide, the content in vegetables. The gas chromatography is used for the analysis of pollutants in air. Thank you once again.